The frequently used transport equations for mass, moles, momentum, and enthalpy have terms in them that can be parameterized by what we call rate equations. We'll begin by parameterizing the flux terms. The rate equations used to parameterize the flux terms are constitutive equations. Recall that the total mass balance equation does not have a flux term. For the component A mass balance equation, the flux term is usually described by what we call Fick's first law of diffusion, which describes ordinary molecular diffusion in either one dimension or in 3 dimensions. The momentum flux term requires parameterization of the shear stress tensor tau. An individual component of the shear stress tensor may be obtained from something like Newton's law of viscosity. The equation for the shear stress tensor for a Newtonian fluid in 3 dimensions looks like this, where the capital T here indicates the transpose of the gradient of the velocity vector. Analogous to Fick's first law of diffusion, we can describe thermal energy transport or heat transfer by Fourier's law of heat conduction, which has both one-dimensional and 3-dimensional versions. All of these can be described as a transport rate being equal to a transport coefficient, either a diffusion coefficient, a viscosity, or a thermal conductivity, multiplied by a gradient, either a gradient in concentration, a gradient in velocity, or a gradient in temperature. While these constitutive equations describe transport rates due to gradients in continuous phases, sometimes we're also interested in describing a flux at a phase boundary. Often the property whose gradient drives the flux, in this case temperature driving heat flux, is discontinuous at a phase boundary. This is true whether it's a temperature, a concentration, or a velocity. Since we cannot take the derivative of a discontinuous function at the discontinuity, often fluxes at boundaries are described by difference equations. Here, the heat flux might be described by a heat transfer coefficient multiplied by a difference in temperature between phase 1 and phase 2. Note that Fick's first law and Fourier's law of heat conduction each have a negative sign in them because the flux is in the opposite direction of the gradient. That is, thermal energy is always transported from points of higher temperature to points of lower temperature, or down the gradient. There are different conventions for defining the shear stress tensor. The convention that we use does not have a negative sign in Newton's law of viscosity. Next, we'll talk about the rates describing the source terms. The volumetric rate of generation of component A, for a system in which A may participate in multiple reactions, can be obtained by taking the transpose of the stoichiometric matrix and multiplying it by the reaction rate vector. In the stoichiometric matrix, each row represents a reaction and each column represents the stoichiometric coefficient of a component in the system, with negative stoichiometric coefficients for reactants and positive stoichiometric coefficients for products. For thermal energy, we already talked about the source term that can be used to describe the generation of thermal energy as mechanical energy or potential energy are converted to thermal energy. Sometimes it is also useful to parameterize or constrain balance equations using equilibrium relations. Equilibrium describes situations where net rates of transport and generation are equal to 0. For transport equations, this occurs when the fluxes go to 0, either the diffusive flux of component A, the shear stress, or the thermal energy flux goes to 0. This most likely happens when the concentration gradients go to 0. Equilibrium assumptions can be invoked when the time scales are large and the length scales are small relative to the transport coefficients. In these situations, the transport is fast compared to the time scale and the length scale of the system being modeled, and therefore the mass transfer or thermal energy transfer or whatever is being described quickly comes to equilibrium. Equilibrium may also be invoked in just 1 or 2 dimensions. This can often be done to convert a partial differential equation into an ordinary differential equation. Consider again our example of a general control volume represented by the gas bubble. Suppose that gas is diffusing inside the bubble, but because of symmetry, we only care about the gradient in the radial or the r direction. That is, the transport in the theta and phi directions we assume are in equilibrium. This is a useful assumption for converting partial differential equations to ordinary differential equations. Chemical equilibrium occurs when the rates of forward and reverse reactions are equal. If the rate of the forward reaction is equal to the rate of the reverse reaction, there is no net change in the composition due to this chemical reaction. This condition is described by an equilibrium constant for the chemical reaction. The equilibrium constant is formally a dimensionless number that can be computed as the exponential of minus the standard state Gibbs free energy of the reaction divided by RT. It's also equal to the product of the activities of the reactants and products, each raised to a power equal to their respective stoichiometric coefficients. Recall that the activity can be calculated from various measures of the composition by taking an activity coefficient and multiplying it by a mass fraction, or an activity coefficient for concentration multiplied by a molar concentration divided by a standard state concentration, or an activity coefficient for partial pressure multiplied by a partial pressure divided by a standard state partial pressure. Activity is a dimensionless quantity, and the equilibrium constant is also dimensionless. However, sometimes the equilibrium constant for a reaction is also defined as the rate coefficient for the reverse reaction divided by the rate coefficient for the forward reaction. This ratio of reaction rates may not be dimensionless, and what we call case of R, the equilibrium constant computed from a ratio of reaction rate coefficients, is not equal to the thermodynamic equilibrium constant defined as the product of the component activities. Phase equilibrium occurs when two phases are in either mechanical, thermal, or chemical contact. For mechanical phase equilibrium, the pressure in phase 1 is equal to the pressure in phase 2. For thermal equilibrium, the temperatures in the two phases are equal, and for chemical equilibrium, the chemical potentials of all of the components in each phase are equal. Often we don't use chemical potential when writing these phase equilibria relationships. Instead, we may describe them by things like Raoult's law or Henry's law that you're familiar with from CBE 201. Remember that the term equilibrium does not mean steady state. Steady state describes a situation in which process variables are not changing with time. That is, their time derivatives are zero. In equilibrium, transport and production rates are equal to zero. Steady state refers to a time derivative being equal to zero, whereas equilibrium refers to a transport or a production rate being equal to zero. We can operate continuous stirred tank chemical reactors and distillation columns at steady state, for example, but if the process is occurring in the reactor and the separator were at equilibrium, then nothing would be happening. The reaction rates in the vessel would be zero, and the transport rates between two phases would be zero in the separator. And for continuous operations like these, steady state may be good, but equilibrium means nothing is happening. Therefore, while we often design them to be operated at steady state, we also design them to be operated far from chemical or phase equilibrium. So why is the equilibrium condition important if we don't often operate there? Well, even when we don't want to operate at equilibrium, it's important to know what the equilibrium condition is, because there is no driving force for transport or chemical reaction at equilibrium. Equilibrium tells us the direction toward which spontaneous processes will evolve. The equilibrium condition also often represents a limit. Rates of transport and rates of production can never take a system past the equilibrium. The equilibrium can also provide targets for improving operation. Sometimes the equilibrium condition itself can be changed by operating, for example, at a different temperature, pressure, or pH to change a rate of reaction or a rate of transport.